well then the square of both sides, okay, must hold. Okay, so from this particular fact, we must have that 2 is equal to a over b squared. Okay, which means that 2 must be equal to a squared over b squared, which says, in this case here, okay, if we multiply across by b squared, that 2b squared must be equal to a squared, if that makes sense. Okay, so that's what we know here, yeah, is that 2b squared must be equal to a squared. Okay. But what we got here from the division algorithm perspective, if a squared is equal to 2 times b squared, okay, well then what that's saying to us here is that clearly, okay, so what we have is that well, we must have that. Well, this is an even number here, isn't it? 2 times any number makes it an even number. So we must have a squared is an even number. Okay, so clearly, okay, from this particular, let's say, the deduction, okay, we have 2 divides 2b squared, okay, and because these are equal, 2 must divide a squared. Okay. Now, what we've shown earlier on, okay, is that if a divides b, well then a divides the square of b. Okay, so if a divides the square of b, well then a must divide b. Actually, we probably should have done this the other way around. Okay, that if a divides the square of b, well then that a divides b. Okay, but what we have here is that 2 divides a squared, so therefore 2 must divide a. Okay, if that makes sense. So 2 must divide a. In which case, okay, 2a must be even. A must be even. Okay, and now because a is even, that means a can be written as 2 times some other number. Let's call that k. Okay, so what do we have from this particular fact here? Okay, so let's call this from 1. Okay, so from 1, okay, we have that 2b squared is equal to a squared. Okay, which makes a must be even from this particular logic. Okay, so that means a can be written as 2k. Okay, so therefore we have 2b squared, okay, must be equal to 2 times k squared. Okay, which means that 2b squared must be equal to 2, okay, times, well, it actually must be equal to 4 times k squared, which means that b squared, okay, must be equal to 2k squared. Okay, but what does this tell us? Well, look over here. What we've said is that a squared is equal to 2b squared, and this fact came from assuming that the square root of 2 could be represented as a rational. That a squared was equal to 2b squared, and from this we deduced that a squared was even. Okay, which means that a must be even because the product of 2 even numbers, yeah, the product of 2 even numbers gives us an even number. Okay, so a must be even. In other words, a can be written as 2k. So a is even. A is even. This is important, okay? But what have we shown here? We've shown that b squared is equal to 2k squared, okay? So b squared being equal to 2k squared, okay? Well, therefore, we have, okay, b must also be an even number, okay? So b must also be an even number because we have b squared is equal to 2k squared, okay? But hang on a moment. What we've just shown here is that a is even and b is also even. Well, then that means that 2 divides a and 2 also divides b, which is a contradiction because earlier on when we said that the square root of 2 is equal to a over b, we assumed that there was no common factors between the a and the b. We actually assumed that the GCD, okay, of a and b, yeah, was equal to 1. Now, what we've shown here through this particular derivation, okay, is that we've shown that a must be even, okay, and we've also shown that b must be even. Well, if both of them are even, that means that there's a common factor of 2 between both of them, yeah, which contradicts our choice of a and b, okay, that we made earlier, that a and b have no have no common divisors, yeah, okay. So this is a contradiction. Okay? And this contradiction has arisen, okay, from us assuming that the square root of 2 can actually be represented as a rational number. Okay, so this contradiction, yeah, arose, yeah, okay, due to our choice of a and b, and more importantly, that the square root of 2 was equal to a over b. Okay, so it's a contradiction. So what this is saying is that if we assume the square root of 2 can be written as a rational number, that what we get is a contradiction. Okay, so this must not be the case. So the square root of 2 must not be able to be written as a rational number, and therefore we have the square root of 2 must be irrational. Okay. I'm actually just conscious here, yeah, okay, that preliminary lemma, okay, which probably is important, yeah, for something else, actually doesn't work. Actually, what I actually required here is just showing here, yeah, that 8 squared was in fact even, and then also showing from that particular fact that a squared was even, that a must be even because the product of two even numbers is always even. Okay, that what we get is that we get b squared being an even number, yeah, okay, and that being our contradiction. Okay. So guys, once again, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was in some way intuitive, and more importantly, I hope that was helpful for you, and thanks for watching.